We're now going to continue this demo on the 3D mapping, and we're going to address the issue of nesting. So what we did in the previous example, we took this three-dimensional temperature field, which is on this North Pacific grid, and we mapped it using the OA 3D into this regional grid in the Northeast Pacific. And this is in fact the surface temperature for the for the destination grid. So we're going to refer to this large grid as the source grid, or the source volume, and as the regional grid as the destination grid, or the destination volume. So when we do this type of three-dimensional mapping, or nesting if you like, in that we are nesting this grid into this larger North Pacific grid, we have to kind of figure out whether this 3D objective mapping will actually give us reliable results. So let's look how we can quantify a little bit of the scale of this three-dimensional objective mapping. So let's go back into the 3D mapping here. Let's go in the ROM's mapping place where we have our examples. Let's open BI 3D mapping.m, and let's now go to the last tutorial, which is tutorial number 5. So that's the one. Okay, and let's check our results. Well, the first thing that I can do is I can look at vertical sections, of the temperature field, for example, in both the destination grid and the source grid. So I can use now, for example, a function called Rnt Section, and the Rnt Section function wants the longitudes, the latitudes, the ZR, which is the depth of the sigma coordinates. Then it wants the temperature, the three-dimensional temperature, and multiplied by the mask so that the land values are put to 0. And then it wants the x, y, which are the location of the transect for which I want to produce a transect. So, and then opt array. This opt array has two values: opt interp, which is the type of interpolation when you map the vertical section, and the resolution in kilometers. In this case, I used 15 kilometers. So for example, here I define two sections, one that goes from longitude -140, latitude 40, to longitude -120, latitude 40. So it's just a transect along longitudes, and this is in the California current, for example, and this is another transect in the Gulf of Alaska, just for fun. So let's start with the first transect, for example, and let's define these array here. Then we go in 3D mapping, and we're going to make a figure now and just plot a section along the transect, both for the temperature that we just interpolated, which is the destination temperature, and also for the source temperature, which is the one for the North Pacific. But we're only going to plot along that section so that we can compare the two. So let's go here in MATLAB, and let's just paste this piece of code. And so now the one on the top here is the section of the destination grid. So this would be the Northeast Pacific grid, and this is the section, the equivalent section from the North Pacific grid. So as we look at this, the first thing that we notice is, of course, there's the topographies are slightly different. The North Pacific grid is very smooth here, as you can see, whether this one has some kind of different type of terrain, although this is region that is landmask anyway. So really, if we focus on the regions where there's water points, they look pretty much the same, although the slope here we'll see is maybe a little bit different. And the rest, they look pretty much, to first eye, they look kind of the same. However, if you start looking a little bit more carefully, you note that in this region here, for example, this particular interpolation, this is the nested grid, the destination grid, has this isotherms that are sloping up here, whether here these isotherms are sloping down. If you think of geostrophic flows, this would mean that the flow here is going in a different direction than it is in this, down here. So this actually could be not very, very good in this particular case. And so how do we? This is one example. Let's look at the other section first. The other section is the one in the Gulf of Alaska. Okay, so we're just going to do that. Go in MATLAB, and we're just going to paste this. Now in the Gulf of Alaska, if if we look along the slope here, where we expect things to be more unmatching, we find that they look pretty much close. The slope is very similar. Maybe here it's a little bit steeper, but it's very similar. So there is a difference between the figure here in the California current, where we have this up tilt here compared to the one in the original grid, and the one in the Gulf of Alaska. So what's different between these two regions? Why is it that in the California current, this interpolation of volume doesn't seem as good as it is in the Gulf of Alaska? Well, obviously, one thing that we have to consider is that maybe if we carefully look better, there are regions here, especially close to the coast, where the topography is perhaps different, in that one particular grid may actually be deeper than the other. For example, here you could see by eye perhaps that this particular region here, the topography is actually deeper than the destination, than the source grid, meaning that it's going to be difficult to extrapolate. You have to basically extrapolate at depth. So how to find these regions? Well, let's go back to our example here. So what we're going to do first is we're going to get the topography of the parent grid, or let's call it the source grid, and we're going to map that into the destination grid, the nested grid, so we can get a sense then of where the topographies are different. Okay, so I'm just going to do this as a linear interpolation here. So this interpolates the topography of the source grid into the destination grid. Then I'm going to take the difference between the topography of the source grid minus the topography of the destination grid. This means that where this difference is positive, then it means that the source grid is deeper. So that means that it contains, that means that the nested grid is contained within the source grid. On the contrary, if this difference is negative, then means that the depth of the nested grid, or if you like, the destination grid, is actually deeper than the topography of the originating grid, and in this case the North Pacific. So that means that in those regions you actually have to extrapolate with depth. So that's more likely to be regions where you are prone to errors. Okay, so I'm just going to make this array here, and I'm also going to assign a value of 0 to all those points where we're on land, so that I don't care about the land points. I'm just going to set them to 0. So let's execute that. Okay, and now I'm going to make a map of this difference here, p color, and when I do this map here, I'm going to put the axis to be from 0 to minus 300, because we only care of the regions where the difference is negative, meaning that the destination grid is deeper than the source grid. In other words, the volumes the volumes of the destination grid is not contained within the volume of the source grid. And in addition to that, I'm also going to plot some lines representing the transect that we just plotted, the vertical transect, so we could see where these transects are occurring. And so let's do that. I'm going to make a figure here, and then I'm going to plot this stuff. Okay, so let's look at this map. The first thing is we find this region here is all zeros. Okay, this is the land. The other thing, we find that there are regions where this is white, and these are regions where the source grid, meaning the North Pacific grid, is not defined. Okay, so these are regions where when you do the interpolation with the objective mapping, you have to extrapolate. Okay, so in space this would be in horizontal extrapolation, and for this particular mismatch here, these white regions here, which are NaN values in this particular plot, that's not too bad. You could see that with the 3-degree extrapolation, the correlation length scale, you will cover most of this stuff, so it's not to worry. So now let's look at the imbalance and the mismatch in the vertical, and these regions of blue area represent locations where the depth of the destination grid is much deeper than the depth of the originating grid. And so you can see, for example, in this transect of the California current, you could clearly see that in this region close to the coast, where we're seeing those slopes being different, you find this very dark blue, which means this is going to be a region where you're very likely to prone in errors, because the difference in topography here is over 300 meters, as you can see in this thing. So that means that the the nested grid is deeper, 300 meter more than the one. And so if we go back to look at the vertical section, you find that there's a region here close to the coast, probably in proximity or where these gradients or these slopes are not very good, where this NEPD grid up here is much deeper than the North Pacific grid. Okay, so that explains why perhaps you find these sloping things in this region over here. On the contrary, if we look at the Gulf of Alaska, this section that I picked here, you find that it's mostly zero. So this is a region where you don't expect large errors. If we look over even more at this map, you find that there are other locations, for example, here close to the Hawaii regions, where there's a big imbalance in volume, in depth in particular. And so you would expect that these are also regions where the error would be very high. So what to do? In this case, I wouldn't feel confident of using this nested solution. So one thing that one could do in principle is to change a little bit the topography of the destination grid, in other words the nested grid, so that these differences are smaller. Or alternatively, you can try and run anyway and see how bad your solution is. But this just gives you some kind of criteria of how to actually check or get a sense of whether to trust this three-dimensional nesting. Okay, so this is all for this tutorial, and for entire section of these tutorials on 3D mapping. And once again, these examples are contained in these tutorials that are contained in this file here, main 3D mapping, in the directory ROMS mapping. Okay, thank you very much.